Okay, YouTube, in this video we're going to confront systems of linear inequalities. Up until now, my videos have been covering systems of equations in which we graph both equations and we attempt to find any solutions that both graphs have in common. Well, when we deal with systems of linear inequalities, what we're going to have to do, since we graph a line but also shade on one side or other of the line, is we are still looking for common solutions to the system. So we're looking for any points that would be on both graphs of both, say, solution sets. But these are going to be overlapping sets. And so our job is to solve the system by looking for what we call the feasible region. Okay, so let's go ahead and start by defining what we mean by feasible region. We say feasible region. Another name for the feasible region would be the solution region for this. Okay, so we say it has a solution region. There will not be just one point that satisfies this, but we'll have a whole set of points that do that. Okay, so let's go ahead and start by taking a look at their sets of solutions by graphing both of these. You'll notice that both of these are written in standard form, so it is very convenient for us to go ahead and just find their intercepts, graph these by the intercept method. So for the first constraint, we'd say if I plugged in 0 for x, I would get 0 plus y equals 6, and I say equals because we're going to graph the line here, but I get a y value of 6. When I plug in 0 for y, we also get an x value of 6. So these are both points on my graph here. I'm going to go ahead and put those in. So I say 1, 2, 3, 4, 5, 6. That's my x-intercept. We say 1, 2, 3, 4, 5, 6. This is our y-intercept. And we can go ahead and graph this line through this. Now I notice that it's less than or equal to. So we're going to go ahead and draw a solid line. And I hope you also notice that drawing this by hand is probably not the best way to do it because you don't have a straight edge available to you. It's imprecise. So we do want to label this. And when you do label an inequality, recall that you label it with an equal sign because we're just labeling the points on the line. We're not labeling the shaded region. So go ahead and find the intercepts of this second graph down here. We say x-intercept, plug in 0 for y. So we say plug in 0 for y, get 2x is equal to 4, so x is 2. And we say plug in 0 for x. We say, well, then negative y equals positive 4, so positive y equals a negative 4. And so its intercepts are down at negative 4 on the y-axis, so that'd be right here, and also positive 2 on the x-axis. And so we're going to go ahead and connect these dots right here. Try to do this as cleanly as I can. So this would be this constraint. As a matter of fact, I'm going to go ahead and delete that because recall that when you graph an inequality here, that you have a greater than, you draw a dotted line or a dashed line. I was getting ahead of myself there. So we have this dashed line. We still want to label this. Recall that it is dashed because we have something that is not greater than or equal to, but only greater than. So we say 2x minus y, we're going to write equals 4. So now, just like we would with a normal, say, linear inequality, we're going to go ahead and test the point for both of these and then shade in the feasible region or the solution region to this. So testing a point, I notice that 0, 0 is a candidate because it is a point that is on neither of these constraints, these lines, okay? So when we plug 0, 0 into the first constraint, I notice that I get 0 plus 0 is less than or equal to 6. Of course, this yields the statement 0 is less than or equal to 6, and this is true. So this is why we labeled, first of all, this line, because I know that I am referring to this constraint, and that made it true, so I'm going to shade on this side of this constraint. The second thing I want to point out is, and this is something you have to do, but I use little arrows to indicate which side of this constraint that the solutions are on. So all the solutions are on this side, notice, okay? So now since we have a system, we have to find the solutions that both of these constraints have in common. So at this point, I just want to kind of point this out. Where could the solutions to this system possibly lie? And so far, we'd say, well, it's to the left of this line for sure, but it might be to the left of this dashed line. And in that case, it would be this little overlapping region where they both shade together, okay? Whereas if it was to the left of, say, this line here, but to the right of, say, this dashed line, you'd have this solution region that's over here. Either way, we're narrowing it down, essentially, is what we just did. So we're going to go ahead and look at which way we would shade on this next constraint. We'll go ahead and plug in 0, 0 again. This is really easy to do because I get 0 on the left, and I'd say 0 is greater than 4. 2 times 0 minus 0 is 0. So we say this is a false statement. And so this constraint right here, it would shade away from 0, 0. So we'd say, well, if it's shading this way, really what we're looking for is, again, we say the feasible region, or the solution region. So we're going to shade this, first of all. You can shade it here. I usually don't shade it in. I just leave my arrows, and I trace an outline. Okay, so this is what I would recommend you do. Trace an outline around the outside of this feasible region. But a few things we want to do before we move on, we're going to comment on these. First of all, we say this is an unbounded feasible region. And the reason why it is unbounded, you think about the root word here is bind, you know, to hold in check, to kind of surround. So this is something that will decrease forever and ever. So for instance, you could always find a smaller point xy in this region it would decrease without bounds, so unbounded. Also this, we look for what we call vertices of the feasible region. And so I've got this point right here that, for right now we just need to know it's called a vertex, but we'll just know that it's the corner point of a feasible region, okay? We do not need to find that for this example here. Let's go ahead and take a look at example number 2. You'll notice that we have more than one constraint in this system. So we're going to start with these first two. These are very common, and I say common because often when we deal with application problems, we're dealing with non-negative things. So whatever x and y represent, they have to be greater than or equal to 0. And of course, this x equals 0 would be this vertical line. Of course, it's greater than or equal to 0, so that is this solid vertical line. So we'll label this x equals 0. We'll go ahead and label our y is greater than or equal to 0 line by graphing the line y equals 0. Okay, label it that way. And then we have to graph this third constraint. Now I notice here that 7 is not divisible by 2 and not by 3. And I only say that because if I'm going to do the intercepts, I'm going to get some decimal values, which means this system gives us a solution region that's not very clearly defined. So let's go ahead and look at this. We plug in 0 for x. Notice that our x is right here. So we have 2 times y equal to 7 when we do this. And then we get y is equal to 3.5. So our y-intercept is 3.5. We'll plug in 0 for y. So in this case, we would have 2 times 0 plus 3 times x is equal to 7. So 3x is equal to 7. We'll divide both sides by 3. We can ignore this term here. So we say 7/3. This would be 2 1/3. So 2.33 repeating. So let's go ahead and draw these points in here. We say 2.33 comma 0 is approximately right here. And then 3.5 comma 0 is approximately right here. So this would be our third constraint, and it looks like this, okay? And we need to label it also. We would say that clearly this is 2y plus 3x is equal to 7. So now we're going to test the point on all these. Now the thing is, with these first two, we can't test the point 0, 0 because 0, 0 happens to lie on those constraints. So we could certainly test any point that's not on that, but I think it's intuitively obvious that we're talking about things that lie in the first quadrant if we are talking about non-negative x's and y's. So I can draw on the rest of these arrows here. You can see it like that if I draw them in. But you can see that they come together up here. We just need to decide what side of this last constraint to shade in on. So let's choose a point to test. It looks like we can test 0, 0 because it's not on it. So we say 0 is less than 7. And I get a true statement. So this is going to shade this way. So what we're looking for here is the feasible region. And that feasible region is this bounded triangular region this time. So we're going to label this, we say it is a bounded region. Okay? And it is also called the feasible region. Okay? It didn't fit in there, sorry. And it also has how many vertices. I want you to think about this. It's a triangle. So how many vertices or corner points does this have? Looks like we have one here, we have one here, and have one here, and we need to be prepared to solve for those things, okay? So in the next video, we'll talk about how you do solve for those and also how to apply this information. Cheers.